Hello. Today's lecture is going to be on parallel resistive circuits. This is the lecture to follow series resistive circuits. And so, if you remember the rules from series circuits, they're going to be different now that we have a parallel circuit. But if you look at this first diagram, if we got rid of these two, we're going to start to call branches, then right here, we still have a series circuit. But as we add branches or add these resistors in parallel, we're going to start to have some new rules because we're going to start to have different paths. If you think of each of these branches as a path, we're going to have different paths for current to go down or for current to flow. So one way to think about it is, let's think of it like driving for a second. I am a terrible artist, so this is going to be a terrible car. But if you were driving somewhere, and if we still thought about this as our series circuit, and you only had this road to go down, then that's the only way you're going to go, right? Like a NASCAR oval. You're only going to go down there. That's the only way current would flow. But if these dots, which are called nodes, if we think of these nodes like a traffic intersection, well, as cars start to drive up to the intersection, some could go down this way, and some could keep going and then go down this way, and then other cars could go all the way around like this. And that's how current starts to behave in a parallel circuit. There's multiple paths, there's multiple branches for current to go down. So in a series circuit, we remember that the current is the same throughout the circuit, even if we added more resistors. It's the same current. If you added more resistors, there would be less current. But within the circuit, and at any point, the current was the same. Not so with parallel circuits. In parallel circuits, we're going to start to get new rules for our Ohm's law variables. And the first one is going to be for voltage. So this is for a parallel circuit. E equals V1 equals V2 equals V3, so on and so forth. And once again, that subscript, just means, the voltage across branch 1. So if we hooked up a voltmeter on the corners of branch 3, for example, and we have 120 volts, then we're going to have 120 volts here. So you can think of it also as the volt drop across each branch is 120 volts, right? The difference, the potential difference from the start of branch 1 to the end of branch 1, if we think of this is the start and this is the end, is going to be 120 volts. So voltage gets a bit simpler once you find one voltage as long as it's all parallel, then you get all your voltages. Okay, so that's a new rule for voltage in a parallel circuit. Now, this is the same circuit again. This is a ladder diagram. It's the same circuit. I sometimes find ladder diagrams a bit easier for understanding parallel circuits. And if you ever don't get a diagram, don't be afraid to draw one. It'll help you understand the word problems a bit better. So if we look at current flowing, it's going to come from the negative. It's going to come into the start of the circuit, and then it's going to branch off into each branch. So it's going to go that way, it's going to go this way, it's going to go this way. But after current flows through each branch, it's all going to meet up at the same point because of how this circuit is connected, because it's connected in parallel. So it's all going to be here. So as we're labeling our different I values, or our different currents in a parallel circuit, at the beginning we would say I total. And since they all meet up at the end, that's also I total. But I1 is going to be possibly different from I2, which may be different from I3 in a parallel circuit. So our new rule for calculating total current will start to look like this. I total equals I1 plus I2 plus I3. Because the current is not getting lost, it's not disappearing as it goes through each branch. We'll learn later that there's a bit of a loss due to heat, but for now, just to get the principles down, as those electrons start to flow, as those particles start to flow into this circuit and it splits off, they're still going to continue to flow from negative to positive, just like in series, but now it has multiple ways to go. So it's going to split up. It will take the path of least resistance. So whichever resistor is smaller, whichever resistor is less in value, which would mean it has less resistance, is going to see more current flowing through it. So let's look at how resistance will behave, because resistance is going to behave a lot different in a parallel circuit than it did in a series circuit. So because in a parallel circuit, current has, options of where it can go, it's going to choose the path of least resistance. So the lower the resistance, the more current, right? Just as I said. And because of that nature of how current's going to behave, if you remember in a series circuit, as we added resistors, we added resistance because R total equaled R1 plus R2, so on and so forth. So if we added an R3, there's just going to be more resistance. We just added another number, right? So R total is going to increase. But in a parallel circuit, because there's multiple ways for current to go, every time we add a resistor, or every time we add a branch that has resistance, so if we add a resistor in parallel, like if we add one here, that's going to give our current another option, and that's going to lower resistance. Resistance is going to go down as we add resistors. That is, total resistance will go down as we add resistors in parallel. So if you remember that, just that basic Ohm's law, E over R, and that inverse relationship between R and I, that means in a parallel circuit, as we add more resistors in parallel, R is going to go down, and we're going to look at those formulas, which means if R goes down, I goes up. So the more resistors we add in parallel, the more current we can potentially have. So your module is going to give you two different ways to write R total. And I'll show you guys how to punch those into the calculator. But I'm also going to give you a third option that it's easier because of the fact that it's harder to make a mistake in the calculator. Because the more buttons you got to hit on the calculator, the more possibility there is to make a mistake in your calculations. So one way that the module shows you how to calculate total resistance is R total equals 1 over R1 plus 1 over R2, so on and so forth, which would look like for this circuit. So this formula in your calculator would look like For this circuit, for example, let's take this 6 and 12 ohm resistor. That's going to look like 1 divided by bracket 1 divided by 6, which would be our R1, plus bracket 1 divided by 12, close bracket, and that's going to give you 4. Another way that you could write this same formula is 1 over R total equals 1 over R1 plus 1 over R2, so on and so forth. And so that's going to start to, it sort of simplifies it in a sense where there's fewer brackets in the beginning. You would take 1 divided by 6 plus bracket 1 divided by 12. It's going to give you a decimal, and then you would take, keeping that same answer in your calculator, you would just go 1 divided by, and then on mine it's the second function, or sorry, it's the alpha function. Oh, that's going to give me a whole. So if we go back up to that, if I go 1 divided by alpha answer, that's going to give me 4. So it gives me the same answer. It's just doing it in 2 steps, or at least I'm doing it in 2 steps on the calculator. What I'm not going to say what you have to use, but another option, a sort of simpler option for a formula, at least in terms of entering it into your calculator, is R total equals, big bracket, it's the only bracket for this one, R1 to the negative 1 plus R2 to the negative 1, so on and so forth. And what that starts to look like, even though it's a bit more unfamiliar if you're not used to using exponents, especially negative exponents. So what that becomes with the negative ones is do a bracket, 6, and then on my calculator I'm going to go second x to the negative 1, and on your calculators that x is just representing the number that I've put in. So that was, I'll just do that again in case you need to find it on your calculator. So 6 second x to the negative 1 plus 12 to the negative 1. Oh, sorry. That should be, let me do that again, sorry. So it's 6 to the negative 1 plus 12 to the negative 1. And the whole bracket, my apologies, the whole bracket will be to the negative 1. So there's fewer 1 over, there's fewer brackets, and that's going to give you 4. So that's how I calculate R total in a parallel circuit. Totally up to you how you would like to do it. If you wanted to transpose this to find, let's say there was an R3, I actually drew one in here, I guess, so we'll call that R3, and you wanted to find the value of R3, you would do R3 equals R total to the negative 1, R total to the negative 1 minus R1 to the negative 1 minus R2 to the negative 1, so on and so forth, however many resistors you have, if you're trying to find the missing one. And so the important thing to remember, and the way to kind of make sure you add it up, if you're looking for R total, that is, if you're calculating your total resistance, in a parallel circuit, your total resistance will always be less than your smallest resistor. So for this circuit, our R total was equal to 4 ohms. And if we went with this hypothetical third resistor that I drew into the diagram, excuse me, that would mean that our total will be less than 4 ohms because I added another resistor in parallel. So I like to present this third formula. Calculating resistance in parallel can be something that trips up some students. So now we're going to talk about our old friend, or kind of a new friend, if you're just starting the course, Kirchhoff, who has something to say about current. And his current law is, in layman's term, or at least in my terms, I guess, current in is going to equal current out relative to what point you're looking at. So if you remember his law in his voltage law for a series circuit, it was the voltage in is going to, or the voltage rise, I should say, the voltage rise is going to be lost throughout all the voltage drops in a series circuit. But in a parallel circuit, the total current in, the total current before it starts hitting these branches is going to be equal to the total current out. But it's relative to where you're looking. So if we were looking at the current at this point, it's not the total current, it's basically the current of 2 and 3, because the current is still flowing through these resistors, if we're still talking about this point. We're only adding up the current flowing through these 2 resistors, not this one. So it's not the total current of the circuit. And so I total equaled, I1 plus I2 plus I3. But if it's asking about different points in the circuit, it may not be talking about total current. So that's kind of why I say it's current in equals current out relative to a junction point, or to the point that they're asking about. Because the question might just, pick a spot right here, or pick a spot right here, if it's asking about I at D, or I at whatever they call it, X. You're going to need to take into account all the branches that may or may not be interacting with the current at that point. So at IX, we only have the current from R3. Now, if it gives you a diagram and it's asking about current, I would recommend labeling with arrows to give yourself the idea of, okay, well, the I total's right here and it's dropping down this branch, it's dropping down this branch. So as I come around here, before I hit this junction point, before I hit this node, I only have R3. But after this node, or at this node and beyond, I have R2 and R3. So if it asks you about the current at B, you're going to have 2 and 3, because at B, it's just before it drops down, or just before it leaves this junction to R2. Now let's look at some ways that we connect things. And hopefully, if you've already done some labs in lab class, these pictures in your module will make more sense. It's talking about Kirchhoff's current law, because into the junction we're measuring I total here. If this is our whole circuit, or it's the I total at before this junction. And then after that junction, it's measuring 2 different ampacities, because the current has gone 2 different ways. But if you see how these ammeters are connected, the current would come in on this line and then come back out on this line. And so the meter is measuring exactly this is basically an open circuit right here, but because we have a meter in, the current is going to flow through this meter, get measured, and come back out and carry on its way into the circuit. And then it hits this junction, it does the same thing because we hook up ammeters, or we hook up meters to measure ampacity in series. Whereas voltage or voltmeters, or if you have a multimeter set to voltage or to measure voltage, you're going to hook that up in parallel. And as you see, these two meters are reading the same amount of voltage because they're hooked up in parallel. And in parallel, if you remember from that first diagram, E equals V1, which equals V2. So if you hook up these voltmeters in parallel, anywhere in the circuit, it's going to read the same voltage. So here's another ladder diagram. But with all that theory mumbo jumbo for parallel circuits considered, if we had an open circuit, or if we lost a branch in a parallel circuit, this is why I like ladder type diagrams sometimes, is if that branch goes, then you could just do this. Oh, okay, that one's gone. All I have is this branch circuit now. And since we only had two resistors connected in parallel, if we lost one of them, so if we lost R1 or R2, now we only have one resistor connected. This is going to act exactly like a series circuit. And since we only have one resistor, that would be our R total, so on and so forth. If we wanted to figure out our I total, if there was no open circuit and this was all connected in parallel, looks good. Our I total is just I1 plus I2. And so if we wanted to figure out what I1 or what I2 was, well, E is 120, which means V1 would be 120. So we could quite simply go I, right back to our original Ohm's law formula, I equals 120 volts over 40 ohms. It's going to be equal to 3. So we got 3 amps. And I might even label the nice big current arrow. That's 3 amps coming through this resistor. I2, we're going to do the same thing, 120, this time divided by 60 ohms, that's just 2 amps. So that means at this point right here, I have this current going through this branch. It's hitting this junction D and then going back towards this positive. And so right here, I have 2 amps as well. And then at B, at this junction point, it's going to pick up 3 amps, which means that my I total is going to equal 3 plus 2 is going to be 5 amps. And if it helps, you can just go through and label all these different points of the circuit. So we know that there's 2 amps in here. We know there's 3 amps going through this branch after this junction. We know there's 2 amps here. We know we had a total of 5 amps going in. Okay, so that's one way to solve a parallel circuit. So let's look at a schematic diagram and let's talk about open circuits and how they behave, or how it makes parallel circuits behave. So in that last ladder diagram, I was talking about if you lost a branch, right? Which would be if at point X you had an open circuit. If my pen will stay with me. If you had an open circuit at point X, then you would lose R4. And if adding more resistors in parallel makes the R total go down, because we're talking about parallel circuits, losing a resistor in a parallel circuit will make total resistance go up. But if the open circuit happened at Y, what that means, even though it's after where the current's going to come in, we would still lose both of these branches. Because if we follow the path of current all the way around the circuit, right, so we'd have our I total coming in at the beginning, and then we'd have I1, so we could call this one I2, 3, and 4, right? And then I2 goes through this branch, so this would be I3, 4. Then at X, we would just have I4. But if the current can't continue to go back, if we have an open circuit at Y, then at this point, right, we wouldn't have current flowing anymore. We would just have the current flowing here. And with Kirchhoff's current law, stating that the current out is equals to the current in relative to the junction point, well, if we had an open circuit at Y, I'm just going to take my module to cover it up. That would mean all we have is the current flowing, not 3, 4, would just be 2 at this point, and then it would be coming back, picking up I1 at this point to be I total. So if there was an open circuit at Y, then we're going to lose R3 and R4. So that's how open circuits will affect parallel circuits. This is also, I mean, of course, it's from your module, as all these pictures are. This has a switch, but the switch is only in one branch of the parallel circuit. So if that switch is open, we just lose R1, R2, and R3 are still connected in parallel. So depending where the open circuit is, I always like to just use a hand, cover it up, right? Grab a scrap piece of paper, start to cover up what is now not in the circuit because of the open circuit. And once again, in this situation, we have an open switch, right? R1 is gone. So if we have fewer resistors connected in parallel, we have more total resistance, which of course means, as you already know, we have less current because our resistance increased. We have fewer paths for current to go down. And so our general Ohm's law relationships still apply, right? Ohm's law is still correct, but the values or the variables and how they interact in a series versus a parallel circuit are going to change depending on the circumstances. Hopefully that doesn't confuse you too much. Now, if you remember that voltage divider law from the series circuits, we kind of have a current divider law, if you want to think of it that way, but it's more about the inverse proportions between resistance and current. And so I'm just the module doesn't really go through the transposing, but I'm going to do that because I think it helps sort of prove the math, if you want to think of it that way. Now, V1, if we just look at this circuit, V1 is going to be equal to I1 times R1, right? That's still true. That's still just Ohm's law. Now this V1 is E. So in parallel circuits, if you don't want to write V and you just want to write E, to remind yourself that in parallel, E and V are going to be equal to each other, as long as it's all in parallel. So V1 equals I1 times R1. Then V2 is going to be equal to I2 times R2, which also means This is the symbol for therefore in mathematics, just to save ourselves writing, I guess. So therefore, I1 times R1 is going to be equal to I2 times R2. Okay? And so in this situation, we have I1. We don't have voltage, but we have I1 that we're looking for, and we have a value for R1, I2, and R2. So if you remember transposing from the first module, what we could do is divide each side by R1. Should have given myself more space. But that's going to give us this equation. I1 is going to be, because we're going to eliminate these R1s, I1 is therefore going to equal I2 times R2 over R1. And so we could figure out I1 just by plugging in the numbers, doing our calculation. But what the module is going to carry on with is, and it's a good way to kind of hammer home the concepts, and it's going to help you with the critical thinking of your circuitry and your parallel circuits. We could bring I2 over to the other side by timesing by 1 over I2 on both sides of the equation. And that's going to give us I1 over I2 is equal to R2 over R1. Right? Because we're still sticking to that idea that resistance and current are inversely related. Resistance wants to, for lack of a better term, resist the flow of current, which is exactly why R1, which has a higher resistance, is going to have less ampacity going through it. Oh, pardon me, that's R2. That's probably mislabeled, maybe in your module, but R2, having a higher resistance, is going to have less current going through that branch. So I1 is going to be equal to, if we wanted to quickly calculate this, I2, which is 23, times R2, which is 150, divided by R1, which is 50. It's going to give us 69 amps. So we're going to have more ampacity on the branch with smaller resistance. So having done that transposition on that last diagram, I now know that I can just take I1 over I2, and that's going to be equal to, as long as I keep that inverse relationship, R2 over R1. If they gave me another load, I would know, sure. If they gave me a fourth resistor, I would know, sure. I4 over I3 is going to be equal to R3 over I4. So that's our current divider rule. It's a bit of a proof of concept of that inverse relationship in Ohm's law. And if you have any questions, as always, let me know.